Every time you send an email, check your bank account, or buy something online, you're being protected by a fortress. But this fortress, it isn't made of stone or steel. It's built from pure ancient mathematics. Ideas that are centuries old, but form the absolute invisible backbone of our digital lives. So what is this master key? What is this piece of timeless mathematical logic, discovered long, long before computers were ever even a dream, that now secures our entire modern world? Well, the answer is surprisingly elegant, and it all starts with a very simple identity. All right, let's start our journey with a foundational concept in number theory. Think of it as a mathematical guarantee that makes everything else possible. Okay, so this is Bezout's identity. Now, I know it might look a little abstract, but what it's saying is, well, it's revolutionary. It guarantees that for any two whole numbers you can think of, we can always find a way to combine them to produce their greatest common divisor. It's basically a promise that a solution exists. It's a mathematical master key. But how do we actually find it? And here's the thing. This isn't just theoretical. The extended Euclidean algorithm gives us a practical, step-by-step recipe for finding those x and y values. It's this really efficient process of just repeated division that systematically uncovers the hidden relationship between any two numbers. And this process, it reveals something even deeper about their structure. So this process, it leads us to something incredible, what you could call the very DNA of a number. It's a way to understand its fundamental code. You see, that process we just saw, that repeated division, it's the exact same process used to create something called a continued fraction. And you have to forget decimals for a second. They're really just an accident of us having 10 fingers. A continued fraction is a number's true, unchangeable code. It's a sequence of simple whole numbers that perfectly describes its very essence. To make this really concrete, let's use a brilliant example. Imagine you have 67 Legos and you want to pack them into boxes that hold 29 Legos each. Okay, so you fill 2 boxes, and you got 9 left over. Your first code is 2. Now, here's the cool part. You invert the problem. How many times can your leftover 9s fit into the old box size of 29? 3 times with 2 left. Your next code is 3. You just keep doing this until there's no remainder. And just like that, you've transformed a messy fraction like 67 over 29 into a clean, simple code, 2, 3, 4, 2. Now, I promise this isn't just a mathematical party trick. Way back in the 17th century, the astronomer Christian Huygens used this exact idea to solve a massive engineering problem. How in the world do you build a clockwork solar system? See, the problem he had was that planets have these really messy orbital ratios. But gears need simple whole numbers of teeth to work. By converting those crazy orbital ratios into continued fractions, Huygens could find the perfect simple approximations, like 33 to 137 for Mercury's orbit. This let him build a model with incredible astronomical precision, all using mechanically simple gears.
So, a 17th century clock. What on earth does that have to do with your online security today? Well, this is where it all comes together. This is where we build our digital fortresses.
Okay, get ready because this is the big reveal. On the left, you've got Bezout's identity from centuries ago, and on the right, that's the core equation of modern RSA public key encryption. They're not just similar, they are functionally identical. That mod n part, that just means we're using clock arithmetic. When you divide E times D by n, the remainder is 1. Finding that private key D is the exact same mathematical problem as finding the coefficient x in the ancient identity. And this private key, it actually has a special name, the modular inverse. And the million-dollar question is, how do we calculate it? You guessed it, we use the exact same extended Euclidean algorithm we saw at the very beginning. The ancient key-finding recipe is literally what forges the private keys protecting us today. The entire security of RSA encryption boils down to this one simple, beautiful asymmetry. See, it's really easy to multiply 2 giant prime numbers together to get n, but it is practically impossible to take that n and work backward to find the original primes. And if you don't have those primes, you can't find the private key. The fortress holds. But what if a new kind of weapon came along that could just shatter that defense? And that brings us to the central conflict of our story. Our classical fortresses, as strong as they are, were never, ever designed to withstand a quantum attack. Enter Shor's algorithm. This is the fortress breaker. It's an algorithm designed to run on a powerful quantum computer, and its purpose is simple: to do the one thing classical computers can't: efficiently factor enormous numbers. For RSA, this is a fatal blow. It turns the fortress into sand.
Okay, so you're probably thinking, this sounds like a problem for the future, right? Wrong. The threat is immediate, and it has a name: harvest now, decrypt later. Right at this very moment, adversaries are recording our encrypted communications, storing terabytes of it, and they're just waiting for the day a quantum computer arrives. The moment it does, all of today's secrets will be an open book.
In fact, there's even a simple formula for this risk, known as Mosca's theorem. It's a stark little equation that tells us if we're already too late.
All right, let's break it down. X is the shelf life, how long your data needs to stay secret. Y is the migration time, how long it'll take us to upgrade all our security systems. If X plus Y is greater than Z, the day a big quantum computer arrives, then your data is already insecure. And for many government and corporate secrets, we are already past that point.
So, what do we do? Where do we go from here? Well, this brings us to the frantic race to build the next generation of cryptographic defenses.
But building these new systems, wow, it is not easy. And for a perfect example, you just have to look at the cautionary tale of Cyc. This thing was a leading candidate for a quantum-safe algorithm built on incredibly complex math. Then, in 2022, it was utterly broken. And not by a quantum computer. No, it was broken in 1 hour on a regular old laptop using a clever piece of math from the 1990s that everyone had just overlooked. So the search is on for new kinds of hard math problems. And right now, the reigning champion is a system called Crystal's Kyber. It's built on a problem called learning with errors. Imagine trying to solve a puzzle, but every single clue you're given is just slightly inaccurate. Finding the true answer hidden in all that noise is incredibly difficult for any computer, classical or quantum.
And what's really fascinating here is the performance. Now, sure, these new quantum-safe keys are a bit larger, but the actual operations are orders of magnitude faster. Key generation is around 3,000 times quicker. That's not just an improvement, that's a gigantic leap forward, and a huge advantage for the fast-paced connections that power the modern web.
So when you step back and look at it all, from an ancient identity to clockwork planets, all the way to the quantum frontier, you see that this battle for security is a timeless mathematical war. The fortresses we build and the weapons used to attack them, they're always evolving, but they're all forged from the same fundamental logic, the DNA of numbers. The codes change, but the fight, that remains. And the question we're left with is, what will the next fortress be built from?